The divergence theorem says the flux, the left-hand side right here, equals across a closed surface equals the sum of the divergences over the region enclosed by the surface. So the best way to really learn this concept is to do an example, of course. So let's say f is 2x plus 3y plus z squared z unit. And we're going to be doing it over the region of a cube, x, y, z, are from 0 to 1. So this would be a cube. So first we're going to do it by the divergence theorem, the divergence. So del dot f divergence is 2 plus 3 plus 2z, or 2z plus 5. And you set up the triple integral 2z plus 5 dv. Now, because we're integrating over the volume, we clearly defined our cube. So it's 0 to 1 for everything. So integrating 2z plus 5 would be 2z squared over 2 plus 5z evaluated from 0 to 1, or 1 plus 5, or 6. And then integrating 6 dx dy from 0 to 1 is just 6. We can also do this the long way. So a cube has 6 faces. We're going to have a face in the xy, or 2 faces in the xy, 2 faces in the xz, and 2 faces in the yz, 2, 4, 6. You know, each one has a front and a back. So what we would do is the flux through each face. So integrate over the face f dot n, or rather n ds. So let's start with the left face. Here we're going to have x equal to 0. So I guess it's going from, let's say, zero to 1, 0 to 1, 0 to 1. Something like that. So we're going to have x is equal to 0 for this face. So this is going to be 0 to 1 for both of these, 2x. Remember, f was so we're going to be dotting this with and we're going to be dotting that with negative x unit and then ds. ds in this instance would be dy dz. So these terms are going to go away. We're going to integrate 0 to 1, 0 to 1, 2x dy dz, negative, but x is equal to 0, so this entire integral is equal to 0. Okay, I've redrawn the cube. This is what the cube looks like. So this was the left face with x equal to 0. This is a general idea what the face looks like, the cube. Then we go and do the right, and here x is going to be equal to 1 because now we're integrating from here instead of at the origin. So now we have 0 to 1, 0 to 1, f dot ds, so ds in this is going to be positive x unit dy dz, and that leaves us with 0 to 1, 0 to 1 of 2 dy dz, because x here is equal to 1, so that's just going to be equal to 2. So far we have 0 because x was equal to 0, 2 because x is equal to 1. So now we do the bottom face. Here y is going to be equal to 0. Same things. And now ds is going to be in the negative y direction. dx dz, and we're left with this. Y is equal to 0, so the whole integral is 0. Top face, y is equal to 1, so 0 to 1, 0 to 1, 3y dx dz, and that's just equal to 3, because 1 times 1 times 3 is 3. Now, then we're going to have a front face and the back face. So the front face is now, we're only going to care about the z unit direction, and we're going to be dotting that with negative z unit dx dy, and here z is equal to 0, so this whole integral 0. Now back face, z is equal to 1, so 0 to 1, 0 to 1, z squared z unit dot z unit dx dz. Now we're going to have 1 squared times 1 times 1, or just 1. So we had a 2, 3, and a 5, 2, 3, and a 1, which is 6, which was what our answer was when we took the divergence and integrated over the entire volume. So we can say that the divergence theorem holds true, which we should have known. But yeah, thank you.